Hi class, today's lab or this week's lab has to do with more thermochemistry. This is the enthalpy of combustion for fuels. The calorimeter, last week you would have used a styrofoam cup for a calorimeter. This week, if you had been in the classroom, it would be an isolated, think of like a thermos, a really very insulated box where a reaction would occur, not open to the environment. This measures the heat involved in reactions or other processes by measuring the temp change. So we can't see what's going on inside because it's sealed, but we can pay attention to the temperature change of what was before and what occurred during and after. Of the change, so let me begin again, measures the heat involved in reactions of other processes by measuring the temp change of materials surrounding the process in an insulated environment. And we'll go into that later, what that means. Last week's lab was a constant pressure calorimetry, meaning it was open to the atmosphere, so the pressure inside the calorimeter and outside matched. In this case, it's completely insulated, so it is not open to the atmosphere, so the pressure will change, but it would be constant volume. No volume would be occurring in this. Because it's insulated, no heat will come in or out, as well as mass will not leave. The energy change is measured by temp difference of the water and of other calorimetry parts. This is a constant volume calorimetry and is termed usually as bomb calorimeter. It just is an insulated container, a very well insulated container. It's designed to withstand high temperature and pressure changes and to be sealed and insulated. Bomb calorimeters are very close to a true isolated system. Heat flow in a bomb calorimeter is measure of delta U. That is, delta U in your book is the internal energy of the system. Last week's in constant pressure, because it was constant pressure, it was enthalpy, the change in enthalpy. And here it's the internal it's internal energy. And we have an equation. I'm not going to go too much into this, but it's allowing you to see it's a delta U, which is the change in internal energy, equals Q. You should be very familiar with Q from last week because you had to use it as heat of reaction. And a new one is W. W stands for work. Work the system either does on surroundings, or the surrounding does work into the system. So W actually represents something else, which means the work is pressure times the change in volume. But in this case, the volume is not changing, so the W will be zero inside this container because it's a constant volume. Therefore, delta U, which is change in internal energy, is only equal to Q, which eventually is equal to the change in enthalpy. So we're still using enthalpy, but it came around in a different way. Again, here is the change in energy, internal energy with Q plus W. In some cases, not for this lab, but as you read that might occur in our book or elsewhere in problems, you could have a very small amount of work done. We normally would, for this case, ignore that, which means the numerical value would be so small that we would just not pay attention to it. Make sure that you understand the problem that you're looking at before you just assume that you can just disregard it. Change in internal energy can be assumed to be the same as change in enthalpy in this case. So we're going to just jump right down here. So we are no longer going to refer to change in internal energy. We're going to just discuss enthalpy. Lab flow only discusses change in enthalpy, so we're no longer even going to bring up internal energy. But you should know that this comes around in a different way than the constant pressure. Also, if you read in some books, in your textbook or ebook, it is known, the internal energy is known as delta U, but in other books and elsewhere, it would be delta E. So you need to understand which one you're looking at. Is it delta U, or is it referred to as internal energy as delta E? That's just something for you to be aware of. So here is a picture of a bomb calorimeter. It is completely insulated, and it is a combustion reaction for this lab. A combustion reaction means it's in the presence of oxygen in here. This little compartment is not not with water. It's completely dry, and the Q, because this is combustion, the heat energy is going to go out into the water. We will detect what the changes are through the thermometer, and this is going to stay completely dry. So in a sense, this is insulated. Our sample is insulated from the water, but the whole thing is insulated from the surroundings outside of that. So when you look at Q, which is what we're trying to determine, if it's an exothermic, the Q is going to go outside into the water in this case. So you'll see the temperature increase. If it's an endothermic, then the Q, the heat energy, is going to flow into the system, and you'll see that temperature decline. Again, we can't see what's going on, but we can definitely measure the temperature. And if you were in lab, you would have to. You would take it initial, you would take it during in certain increments, and then you would have a final when everything is stabilized. So heat capacity. The first thing that's different with a bomb calorimeter is that we need to take the heat capacity of the components of everything involved. So the standard to use the total heat capacity of the calorimeter components and the water inside. So last week you looked at the specific heat of water. In this case, we use heat capacity of everything that's involved, the calorimeter, parts, and the water. Heat capacity is the amount of heat required to raise the temperature of a system by 1 degree Celsius or 1 degree Kelvin. We use these interchangeably, so don't be surprised if you see things in Kelvin and not in Celsius. We use this as a big C with calorimeter, or just cal, as you can see down here. That's used to represent the combined heat capacity. And in some questions, you'll actually be given that information. Here, you're going to have to solve for it. It is measured with a known mass of a substance and an accurately measured volume of water inside the calorimeter. The product of those is equal to the heat flow of the solution and the calorimeter, which is an opposite sign of the heat flow of the reaction. So when you see heat capacity, you need to pay attention to a few things. Heat capacity of the calorimeter means that there's 2 units that go with it. It's either joules over Celsius or joules over Kelvin. This is units that go with this. A lot of students have problems with thermochemistry, and an easy way, not an easy, but an effort to understand it more, is understand what the term means and know the units that go with it. Because if you get stuck on a problem, you most likely can help yourself out of it if you know the units that answer should be in. So here is one term we're going to actually jump into right away. It is the Q reaction. This will be Q reaction here. They have it like this, but it's just Q with the heat capacity of the calorimeter and the temperature difference. We need to know this in order to move on with this lab. So here's a perfect example of a calibration sample problem. I realize that this is a new chapter for you. You should have covered some in Chem 10. It's only going to get harder, and you really need to start jumping and reading in on this chapter in order to understand some of what's being stated here. A bomb calorimeter needs to be calibrated before it can be used with your sample. You use 1.325 grams of a fuel, and the enthalpy of combustion, in this case it's known as QG, which is energy density. We'll come to that later because it's something you're going to have to solve in this lab, is negative 52.5 kilojoules per gram. So here's another one. You're going to need to solve for this. You should know the units that go with it, kilojoules per gram. So my answer should be in kilojoules per gram. Or I'm sorry, let me start again. This is QG. You're going to have to solve for it. It's in kilojoules per gram. But that's not what the problem's being asked. I jumped ahead. It's going to be the heat capacity of the calorimeter. So if the water temp in the calorimeter increased by 12 degrees Celsius due to the reaction, what is the heat capacity of the calorimeter? I put this in parentheses. This would normally not be given to you, but you should immediately know, okay, I have to do 2 steps because I'm giving a lot of information here. The first thing, and by the time you get done with this, watching this video, hopefully you'll understand the steps that are involved, plus reading the PDF. You need the mass. You have a mass here, and you're going to need the enthalpy of combustion because we need to get Q. We need to get the Q of the reaction. So I've given you the formula, and these are all in your PDF. So this is the energy density, which will cover mass that's burned. So that's what this is what was combusted. And you set them up. You should know by now that Q reaction is joules or kilojoules, and it is. My answer ends up being in kilojoules. You're going to take this answer, and now you're going to determine the heat capacity of the calorimeter. This is very similar to what I just showed you on the other page. Now, unfortunately, this moved over, and I apologize. This should be with this, and I'm not sure why it changed when I saved this, but it doesn't matter. You can see that this is from here, and it's on top. That's my I isolated this out. So what I did is my Q, I pulled this on this side and put my Q reaction on top and my degree on the bottom. So basically what I did is I brought this over, left this, and then brought the negative sign over. Pretty much isolate C for calorimeter. It's just simple, math that you guys should already know. It's a little confusing here, and I thought I had it set, but I don't know. Anyways, my calorimeter is 5.80 kilojoules over Celsius. So this is another one. We'll get to, in your PDF, it states what you need to find and the units, and this is another one. So if it's asking for the heat capacity of calorimeter, you should know that you have kilojoules over Celsius or kilojoules over Kelvin. I took a copy of our picture of your PDF, and these are the symbols that you need to know. These are the units. This is exactly what I'm talking about. You're going to solve for all three of these in this lab in the second section. You have two parts to this lab. So make sure you understand these or become very familiar with them, or at least the units, so you understand what you're doing. Again, I took another picture here, which helps you understand steps you need to do. And this horrible line that I tried to put together. So Q, you should be familiar with, kilojoules or joules. This Qg is the heat of reaction for 1 gram of fuel burnt. So when you see the G, that's 1 gram. It's also known as energy density for a substance. So it's easier just to say this is energy density. And then you have the change in enthalpy per mole, the heat of reaction for 1 mole of fuel burned. So if you're going to be asked to do a balanced equation in the end, your fuel should always be 1 mole, and I'll cover that later. But when you see these terms, this is always implied 1 gram, 1 mole. These are all actually enthalpy changes, but they broke it up in a different term, so not to get you confused in this lab. Again, you're going to be needing these parts for lab 2, so it would be really handy if you kept your PDF close by to understand what's being asked. And if you get confused, if you know the units, this will help you solve problems. So gravimetric energy density, this is the QG, is energy provided per gram, per kilogram, per pound. You need some measurement for this. If the fuel has a high GED, a smaller mass is needed. So think of this as more bang for your buck. If you have two substances and you want to pay for the one that's better quality, and this is a perfect example of it. If you have gas, you want gas that's going to get you further, not one that's going to burn through faster and have to keep stopping at a gas station. So if you look here, we have an example. You have a substance A that's negative 25.6 kilojoules per gram, and you have a substance B that's negative 35.9 kilojoules per gram. Now, do not get confused with what this means. This is a combustion reaction. These are fuels. So we put fuels in our car, like octane. We use propane, we use methane, we use things. You want high number values. It'll last longer. So do not get confused with the negative in front. Remember, negative and positive is just direction. You actually are looking at the value as a straight value. So you would want one that has a higher value. Why? Because if you have two gases to pick from, you want the one that is better quality, which means it's going to last longer than the one that's lower. You're not going to get as much out of it. So substance A has an energy density of 26.56, and B we can see. Substance B has a greater energy density than A. This means that B will burn less than A to produce the same amount. So think of density. The denser something is, the more compressed it is. So think of it this way. You have two fuels. One is burning slower, which means it's going to last longer. So the numerical value is what you want a higher value of. That's going to allow you to have a drive that longer than substance A would. Here's a problem, a sample problem for you to determine the energy density. This is also 2 steps. Most of these have to be 2 or 3 steps in order to get the answer. Nothing's going to be just flat out. A sample of fuel, 1.50 grams, was burned or combusted in a bomb calorimeter. The water temperature increased by 15 degrees Celsius. The calorimeter has a heat capacity of 5.43 kilojoules per Celsius. So it's already given it to you. You don't have to do that part. Determine the energy density of the fuel. So the first part is you need to know the Q of the calorimeter. So you have the heat capacity, you're given the temperature. So you just plug these in and you get Q, which is negative 81.5 kilojoules. You're going to take this answer and now you're going to determine the energy density. In your PDF, there's two formulas in order to solve this. For this case, you would actually only be able to do it this way because you don't know what the fuel is. So this means Q, the reaction from above, and M means the mass burned, which is right here, 1.50. You plug that in, and this one actually looks right. The units are not moved. Is negative 54.3 kilojoules per gram. This is not a great picture, but it kind of gives you an idea of what's going on. This is not completely accurate, but the idea is. You have two parts to this lab. One, you have to calibrate the calorimeter to get the heat capacity, such as what's here. And then you're going to use that heat capacity to solve for the three things that you needed to do for part two. So here's one example. You have the heat capacity. You're going to solve for heat capacity. You're going to use it. And then you're going to solve for the third part. I have it broken down, so we'll cover that. So in this case, everybody's going to have hexane as their to use as the fuel for calibration. That's not going to change for everybody. However, everybody will have different temperature and different masses. What happens is that you're going to set it up the same way you do here. So this is not completely accurate. It would have a box with the fuel away from the water. It's going to be combusted in the presence of oxygen, so it's a combustion reaction. And you're going to take an initial, and then you're going to take increments, or if you were in lab, increments of the temperature at certain time increments until it's finalized. And then you're going to determine what the heat capacity is by doing this calibration. Then you will all be assigned different fuels with masses and temperatures, and you would do it again the same way. Your fuel would go in here. You'd watch the temperature, take certain increments of time until it's stabilized, and then you would go back, and then this is where the calculations start. So a combustion reaction, you guys should be very familiar with what a combustion reaction means. It usually involves C, a carbon and hydrogen, certain amounts, in the presence of oxygen, which always produces CO2 and water. You should know what a combustion reaction means. What does hydrocarbon mean? You guys may not be aware of that yet, but hydrocarbons mean a carbon and hydrogen, and sometimes oxygen's also involved, but it's usually hydrogen and carbon. That's what organic chemistry is. It's all about organic chemistry is hydrocarbons. Here's a brief little naming here. Methane, this means one carbon, so this would be cut off and there would be an H here. Hexane, which is what you are using for the calibration. Hex means 6, so there's 6 carbons. These names have to deal with carbons, and this would be hexane. And the ane part means single bonded. There's only one bond for everything. So when you hear propane, methane, that's what that means. But anyways, here's the reaction. You will have the general reaction, then you would have to balance it out with this always being 1 mole. You can use fractions throughout the rest of it. So here's a picture, a very bad picture, but a picture of a combustion calorimeter. This is from your PDF. You have the fuel that's going to go here, and it's separate from the water. And the reaction is going to go off, it's going to occur, and then the heat will transfer to the water. There's a temperature probe, and you would be able to collect the temperature from this reaction. So there's 2 parts to this lab, and it's the same for both parts. This would be the same. Nothing would change. You would calibrate the calorimeter with hexane as the fuel, and then you would determine certain values and use those values on part 2. And then the second part, you would all be assigned a different fuel, and then you would solve for these things, which is what I previously showed on one of the other slides. Make sure you know the units. If for any time you get confused on this lab, this PDF is actually a pretty good PDF even if it's foreign. If the more you start reading the chapter and the more you start working on this, it actually explains a lot more steps than some of the other PDFs that I've seen. And this one does a pretty good job. So make sure you thoroughly read the PDF before you even get started, because this is a lot of information. Don't wait till the last minute. This is giving you the energy density of hexane. So everybody, this is where you need to find this information. I even highlighted it here. I don't have the rest of the PDF up here, but I want you to see that it completely breaks everything down in steps if you don't like the steps that I'm going to give you here. So part 1 is the standardization of this should be calorimeter with hexane. So you have a burner, and the burner in this case is hexane. So I took that information for the PDF. I put everything on here that you're going to need to solve part 1. Now, one thing I want to point out, you have a negative sign here. You do not want a negative sign with the mass of your fuel. So you're going to do it opposite this time. You're going to do initial minus final. You should have a positive value. Why? Because you start out with more, you have a combustion reaction, and you lose a certain amount of mass that goes into CO2 and water. So this is where we're going to be able to detect the heat flow that transferred out of the system into the surroundings. We do not want a negative mass here. So subtract your initial from your final to make sure you get that. And then you have a temperature. This is handled the same. There's not a problem with this. Plus, there's more information on the PDF again if you need to go through that. I pulled out the reactions that you're going to need. They all come from here, the PDFs and so forth. But for part 1, these are what you're going to need. You need to determine the reaction from your energy density and the mass burn. So with your fuel of hexane. In this case, you're given this information, which your energy density should be in kilojoules per gram. And you were given the mass through subtraction of the fuel that was used. From here, you're going to get your kilojoules of heat of reaction, and that's about right because this should have 1 unit. Next step, you're going to determine your heat capacity of the calorimeter. So that's the whole step of why you're doing this, is you're calibrating the calorimeter, because you're going to use this information in part 2. So same thing, you're going to have a reaction that's on your PDF, but I have it here. It has a negative sign. Make sure you have the negative sign, and then plug everything in. So we need to solve for the calorimeter. This is what I was trying to show on the last page a couple slides ago. You have your Q reaction, which is here. And then you have your temperature difference, which if you get confused on any of this, I have it all on this one slide, and set it up. This is for my first trial, but I'm going to pretend I did 2 trials, and this is my average for both trials because I only have 1 trial, of course, listed up here. So you will need to do averages. By this point, you should understand how to do averages, and I only did 1 trial, so I couldn't do it anyways. But I'm going to pretend that this is my average of 2 trials. I'm going to determine my percent error. Here is, there's 2 ways on your PDF. It's listed as an estimate way. I did not cover it that way. You also have another PDF that covers accuracy, precision. Percent error is in there. It's normally listed as an actual value and an experimental value. This case, I don't know which is which. So what I did is I took the average. It's similar to the estimation. So is it exact? Not really, but it's close enough that it'll do on either way. You have, because I don't know which is actual and which is the experimental. So I just took the average and then followed the rest of it. I subtracted and took my average and got me my percent error. But if you don't like this way, the PDF speaks about another way to do this. Okay, so now we're on part 2. I was given the fuel methyl T-butyl ether. You're going to have to look up your own molecular mass. They do not give that to you, but they give this part here. I also was given information, so this is my information and any of the equations that you're going to need. You're also going to need your value from part 1, which is exactly what I'm talking about, which is right here. Okay, so let's get started. You need to determine your Q reaction for this fuel. You already did it for hexane, but that was simply to calibrate the calorimeter. So we have our value from part 1. We have it here, and we have our temperature difference for this section of this fuel. And you just plug everything in. I now have my value with my methyl T-butyl ether. And my temperature difference, oh, I have it listed wrong here. That's okay. Pretend this is 5.0. I had 2 trials. I must have mixed them up. Determine the moles of fuel. So N is always representative of moles, and M is representative of mass. Here we want the moles. So we have the mass that was burned or combusted, and then we have our molar mass. So I set that up. I get grams cancel out. It gives me moles, 0.152 moles of fuel. We are not done. Remember, we have to solve for a couple things. So the first thing we're going to solve for is the change in enthalpy of moles. So this is kilojoules per mole. Here we have the change in enthalpy, and it's equal to Q reaction, divided by the moles that were burned or combusted. So here we have what we determined from the first part. We have our moles from the second part, and we simply set them up, and that gives us our, make sure you keep the negative sign, negative 3,118.4 kilojoules per mole. That's one of the things that we had to solve for. Actually, 3 of the things. We solved for one here, we solved for one here, and this is the third one here. The third one is the energy density again. We have our Q reaction. We have our mass burned. We got this part from here, part 1. And now we solved it. We set it up here. We have our mass that was also given to us through subtraction. And now we have our energy density, which is negative 35.73 kilojoules per gram. So those are the 3 things that need to be solved for this lab. It's not too bad, but it is got a lot of details that could be easily missed or not understood if you run through it quickly. Now, I took a copy of it. These are 3 parts at the very, very end. There's one more part, but that part I expect you to do. There's one part above this, which is balancing the equation with your fuel. I expect you to do that with 1 mole, and fractions are okay. I have an example I'll show you on the last page. This question here is asking for the enthalpy of formation. These are one of the last chapters in the book. Because I'm giving you guys a week and a half, I don't expect most of you to get to this point. So I'm going to give you credit for these 3 things. But there's a catch. In order to get credit, you have to not leave it blank. If you leave these blank, you do not get credit because you're not following my instructions. And it's right here. So what do? Enter something. If you need to, just enter numeric values in the 2 boxes and then type something like, hi, how was your day? I don't care for this lab. It won't hurt my feelings. But that's as mean as I'll allow you to go. Just something with a few words. Why? I just don't want it blank. Okay. But the reality is most of you probably won't get to the end of this chapter to cover this section till next week or the weekend. And by then the lab's due. So I'll give you credit for these. Also, if you get a problem on the lab that features this delta enthalpy formation, I will also give you credit for that too. Okay, so my tips with balancing for your equation for your fuel, keep your fuel, excuse me, I apologize, keep your fuel, which I messed up here, as 1 mole. What do I mean? My fuel here is still 1 mole because everything when you see a kilojoule per mole, it's always assumed it's 1, it's a default. You can have fractions on everything else. Usually it's always just oxygen that you have your fraction and just leave it. It's perfectly fine. What you guys are going to do is fractions will end up working out itself when we get to Hess's law and so forth. Don't forget to upload your calculations. I do check them. Thermochemistry is not easy. This is one of the hardest chapters that students have. So make sure to give yourself time. And honestly, you should be working on about an hour a night of this of chemistry. Read your PDF thoroughly and refer back to it if you need help with the calculations. I think the step by step is really good for this lab. It does go, it explains itself better than the other labs that I've seen. If you get a question, here it is again. If you see this little symbol, don't worry about it. I will give you credit for it. There may be in the quiz. These problems are randomly chosen in the quiz portion. I can't control that. If you can, do the data report and submission first, because once you go through the steps of calculation, Here's something that you need to know. The quiz has some calculations on it, and if you don't know what you're doing, you're going to get lost right out of the gate. So if you can do the data report and submission first, definitely do that, because then you will be able to understand, or you will feel a little bit more comfortable answering the quiz portions that have these calculation problems in it. If you get confused with the question, basically what it's asking, try to break it down slowly. And once you think that you know what it's asking, know what those units are. If you know what the units are, you can set yourself up enough that you should be able to get through the steps. You're going to need to look up the molar mass of your fuel. They're very interesting names for some of them. I'm familiar with them. I'm not sure you guys would be, but you'd have to look them up. And here's a hint for the quiz portion. Read over the safety. Make sure you understand it. And honestly, this is a PDF you probably should be printing out, because it'll make it way easier to go through this lab if you're lucky enough to do that. I didn't always have a printer, so I couldn't do things like that. And that's it. So take your time, but don't wait till the last minute to do this. You can always contact me. And this lab ends, of course, on Friday, but this chapter will end on Tuesday. So make sure that you give yourself enough time to do this lab. Okay? Thank you.